Hello future pilots, let's start the next chapter of instrumentation, which is the inertial navigation system. So inertial navigation system is aircraft self-reliant GPS without needing any satellites. But how is INS a self-reliant GPS? So INS uses internal gyroscope or accelerometers on a stabilized platform to track position, attitude like pitch and roll, heading and speed purely from motion changes. So that means that it doesn't require any other external signals to work. So it is perfect for any weather or remote areas. So let's read what's written here. An internal navigation system lets an aircraft figure out its position, attitude, and speed using only internal sensors. That means no external signals are required. The key components are gyroscopes and accelerometers, which are mounted on a stabilized platform. As I said, sensors measure changes in the aircraft's movement, and a computer calculates speed, distance, and direction, and thus providing us the information we need. So now we know that IRNS lets an aircraft figure out its position, attitude, heading and speed using only internal sensors. So now we will see how the IRNS works. INS uses Newton's laws of motion to track movement accurately. Accelerometers measures acceleration in specific directions. So when integrated over time, we know that acceleration, when integrated, it gives velocity, and when it is double integrated, it gives us distance traveled. Alright. So by knowing the starting location or the takeoff location, the computer can keep updating the aircraft position in latitude and longitude. So let me break this down for you. Inertial navigation system uses Newton's law. So accelerometers detect speed changes along north-south, east-west and vertical axes. That means that accelerometers detect accelerations along north-south, east-west and vertical axes. And we know that if we integrate acceleration, we get velocity. And if we again integrate velocity, we get the distance traveled. So what are accelerometers? Accelerometers are sensitive pendulums like devices that swing when the aircraft changes speed. So you can imagine a pendulum. So whenever the aircraft changes their speed, the pendulum swings. Their movement is converted to electrical signals representing acceleration, which are further processed to get velocity and distance data. So what happens is when the pendulum swings, the movement is converted to electrical signals and which represent acceleration. And we know, and you can see here also, that when acceleration is integrated, we get velocity. And when velocity is integrated, we get the distance traveled. You can see from the image also that when the aircraft accelerates, the movement of the pendulum, and when the aircraft decelerates, the movement of the pendulum. So the movements are sent via electrical signals which represent the acceleration, and by integrating we get the velocity and the distance. Alright. So now we are going to study the main parts of the INS. So before only I've said the components of the INS, that it contains gyroscopes, accelerometers and has a stable platform. So we have already studied about accelerometers, that it measures changes in speed along north, south, east, west or sometimes vertical axes. But what is the use of the gyroscope? And we know that we need a stable platform, right? So the use of gyroscope is to keep the platform level and stable. So accelerometers only measure intended movements and not be affected from gravity or tilting. So if the aircraft even tilts or rolls, the platform should be level to get only the intended movements for the use of the INS. And what are the use of the gimbals? So to keep the sensor stay level, when the aircraft tilts or turns, the gimbals are used. Now we know that accelerometers give us the acceleration, but we also have to integrate to get velocity and again integrate to get distance traveled, right? So who does this? It is done by the computers, and it also correct errors and display navigation information to pilots. How the sensors stay accurate? The platform holding the sensor uses gyro to remain earth level. Even as the aircraft moves in different attitudes, if were not stabilized, gravity effect would cause wrong reading. So we can say that gyroscopes are the heroes which keeps everything level, which are mounted with gimbals. They counter aircraft tilts so accelerometers ignore gravity fakes. The integrated gyros arrange perpendicular to each other. Whenever they detect any dip, they send signals to the motors that realign the platform. So as you can see in the diagram, there is a pitch motor, roll motor and azimuth motor. So whenever the gyros detect any tip, what happens is that it sends the signals to this motor, which again realigns the platform, because we know the importance of the stability of the platform. Earth's rotation and correction. So because the aircraft flies over a rotating Earth, certain corrections are needed. So we have already studied about earth rate and transport rate. So there must be a compensation or corrections. So let's read the first one, earth rate compensation. So sensors correct for the a planet's spin with adjustment based on latitude. Next one is transport rate compensation. Sensors also consider the aircraft's movement over the curved earth. Extra corrections fix errors from the centrifugal and Coriolis effects as well as the Earth's slightly non-spherical shape. So let me explain. So flying over a spinning curved Earth, INS has to compensate. So Earth rate fixes planetary spin and transport rate handles path over the globe. And there are some additional fix like Coriolis and centrifugal forces and the Earth's shape, which is not properly round. So to keep the errors low, corrections are made. This teamwork ensures pinpoint accuracy mid-flight. Next, we are going to study about initial alignment before use. So we have to have a initial alignment before we use the INS, because aligning the sensors before flight is crucial for accuracy, because we know that how much important is to keep the platform stable and level, right? So the system first levels the platform to make sure accelerometers sense zero gravity errors, because we know that it should only be sensing the movements which are from the aircraft and not due to any gravity. The platform must be oriented to the true north via gyro compassing. So the platform must be oriented to true north, and via gyro compassing is a process which uses gyroscope to lock onto Earth's rotation. So there are several steps that you have to learn. First one is warming up, then coarse leveling and alignment, then fine leveling and gyro compassing, which takes a few minutes in total. So in short, I can say that before takeoff, INETs need preparation. First, we have to level the platform with the use of gyro compass to true north, and then we have to warm up plus course align, which takes a few minutes. Next, the Schuler's principle. The Schuler tuning concept keep the inertial platform aligned with the local horizon, factoring the Earth's curvature. Feedback signals help the system remain properly leveled even as the aircraft accelerates in different directions. So if it is misaligned, the system naturally tries to correct itself over a period of approximately 84.4 minutes, which is the Schuler period. So in short, I can explain that Schuler tuning mimics the Earth's curve. So it is self-correcting over 84.4 minute cycles to stay horizon aligned. So now we are going to study the types of INS errors. So basically there are two types of errors, bounded errors and unbounded errors. So let's talk about bounded errors first. So these are built up and they disappear within the Schuler cycle, which is 84.4 minutes, and are mostly due to. So basically these are for a short period of time because it disappears after a Schuler cycle, right? So the reasons behind it is that it is basically due to platform being unlevel at start, accelerators measuring inaccurately, and calculation errors in integration steps. So basically you have to learn these points, alright. Next we are going to talk about unbounded errors, which continue to grow with time or distance and include starting heading errors, gyro drift causing heading inaccuracies, and errors accumulating in position tracking due to misalignment. So you have to learn these points. Applications and modern developments. INS provides all critical navigation data to autopilots, flight directors, or pilots which are manually flying the aircrafts. Modern versions may include laser gyros, IRS, which is inertial reference system, for even greater accuracy and reliability. So basically in inertial reference system, they uses laser gyros, which provides next level precision. INS is priced for being self-contained because it doesn't need any outside sources like radio aids or satellites. making it robust in environments where these sources aren't available, like in weather or in remote areas. So now we are going to compare INS with other systems. So INS does not rely on external reference like GPS or radio beacons, like we already know, making it highly independent. However, it can be combined with other navigation methods like GPS or DME for error correction and best performance. So for best performance, what we do is we combine the INS with some navigational aids like GPS or DME, which makes it more accurate and advanced. So this is the last part of the video, advantages and disadvantages. So let us look at the advantages first. So it is precise and self-sufficient navigation. So we already know that it does not rely upon other systems. It works anywhere, anytime, regardless of weather or signal availability, which that makes it self-sufficient, right? Gives continuous updates on position, speed, attitude and more. So the INS provides continuous information on position, speed, attitudes, heading. So now let's look at the disadvantages of the INS. It needs careful initial alignment. We already know this. Errors can build up over time without correction. So we are talking about the unbounded errors, right? And it is relatively complex and costly compared to simpler systems. So these are the disadvantages of the INS. So this is the end of the chapter. You can get these notes from the description itself. Thank you for watching.